Hello everyone! We are starting our free open lecture on our Discord. If you are a viewer and want to ask questions online and get answers, join our lectures. You can find the link to Discord in our Telegram channel. Let's try to make this happen. So, we have this array, we already have everything from the test examples, and we will try to write it. We have some value here, target, and I run this loop a certain number of times. So, for in range, len of r, I am saying that we have some. For example, y, which we are looking for, that equals target minus r and t. In this case, r and t are our x that we are setting by index. Accordingly, for this, what we do is we also write L less than or equal to R, where L is equal to 0 and R is equal to the last element. This is the segment where we will be searching. Next, we calculate the center. L and R are equal to the last element, which is ln of R minus 1. This is the segment where we will be searching. Next, we will calculate the center plus R divided by 2. Then we proceed with the comparison. That is, if our R with the index middle is equal to our target, but not the target, rather some y that we have already calculated. If it is equal, then we return the value. Again, we want to return it, or in this case not return it immediately, but count it. So I write here count equals 0. I want to count. What is happening here? I understand that then we have a pair, and I need to add 1 to the count. Accordingly, in the case when our r with the index mid is less than y, that is, our value is less than the one we want to find, we understand that we need to search to the right. Therefore, L will be equal to mid plus 1. Otherwise, when the sign is greater, R will be equal to mid minus 1. Thus, we will try to find this value. And then, we reach some element in this list. For example, if we want to find the k minus 3 pair of the number 13, it will tell us that the number 13 seems to be here, and we need to compare whether it is actually the number 13 or not. That is, binary search cannot determine whether such an element exists in our array within its algorithm. Therefore, we must compare ourselves whether this element that the binary search points to is the same as the one we found or not. In this case, it is about similarity, that is, exactly equal. Somewhere in the center we need to compare, that is, if R with some index L, because there will be the index L, is equal to...
Want to become a great programmer? Subscribe to our Telegram channel.
If it equals Y, then I add 1 to the count. Otherwise, I don't add anything. And after this algorithm, that is, after the for loop through the entire array is finished, I return our count. So, to solve this problem, we need to sort this obvious array. We need to determine that we have found this element here, and accordingly we should end this loop. However, in this case, we should not add 1 if, firstly, our boundary L has gone beyond the array limits, which is the definition of limits. Also, we should not add 1 if we have already found it in the binary search. In this case, we will not add it. Accordingly, if we have these 3 conditions, that is for pass, and the element R with index L equals Y, then we add 1 and change the flag back to false. Otherwise, we just move to the next one, that is, we define continue. This can actually be omitted since it will move to the next loop for I anyway, and then we return the count. Accordingly, running this program, we get the answer 5. The code turns out like this if we write it all down here. If we want to read all these numbers from a string, for example, we can write it this way and immediately convert it into a list. The target number will be in the next line, for example. So by putting this list and this value, it will give us all the pairs that we can identify in the array so that the sum equals the target. The next case, which is our third solution, is determined through dictionaries. The first thing we do is determine which numbers and how many of them are in the array, and we write all this into a dictionary. If I copy this array, we don't need to sort it here. I will get such a dictionary. The number 1, its count is 1. The number 2, its count is 1. The number -1, its count is 1. The number 4, its count is 1. The number 7, its count is 1. The number 3, its count is 1. There were no larger numbers before. The number 8, its count is 1. The number 11, its count is 1. The number 9, its count is 1. The number 2 was already there, so I go here and add 1, so we get 2 counts of the number 2. And accordingly, I just have 1 minus 3. Accordingly, this is how I understand that we get these quantities for the given numbers. And what I want to do next is to iterate through the entire list in the first cycle and fill a dictionary with the counts of the numbers. The purpose of filling this dictionary is to have a quick reference for the counts of each number, which will be useful in the subsequent steps. Then I determine that if we are at 1, what I want to find in the dictionary is if there exists a number which we need to check, that is the target -1. For example, if there is a 9 in the keys and we have a 9, we simply add the multiplication of this one by 9. This means that for every occurrence of the number 9, we will multiply it by the count of ones and add this product to our total. I hope this is clear, meaning we add these quantities to get the final result. But again, we need to remember that if we encounter a 9, we will add all the ones for it. This ensures that we are accurately accounting for the contributions of each number in our calculations. Therefore, we can definitely add ones for each number and subtract ones from the count. That's basically it, so that we don't have such numbers. And what will we subtract? We will subtract both 1 and 9. In this specific case, it is generally about the presence of pairs, meaning that additional conditions here are that we do not care about their order. So, for simplicity of execution and implementation, we will write it in such a way that both 1,9 and 9,1 can be counted. We will slightly change the rules here so that this algorithm, which is not entirely relevant to this topic, can be simplified. Therefore, we will specify conditions such as 1,9 and 9,1 being acceptable. Accordingly, we will complete this algorithm. We have some kind of dictionary, meaning a dict. We iterate through the array, we have a target, and if our value, meaning some r and t, is already in it, then I add 1 to this value. Otherwise, I need to add it here. In conclusion, we have successfully modified the algorithm to set it to 1, that is, to actually create such a key value pair in our dictionary. What I do next is all of this. The complexity of the operation is 1 for, that is, on, based on the length of our array, where n is simply the number of elements in the array. In this case, I simply go through the range of len of r, and accordingly, I understand that, for example, I will write here with a bit more extra code that x is equal to, or rather y is equal dot to target r et, and accordingly I need to set some count for counting here. But again, we need to ensure that it exists. That is, if y dot is dot in dot this dictionary, and there are some counts. There we dot need to compare dot comma for dot example comma comma if dot it dot is there, and we dot can remember. The index dot or dot it comma is not very important. If it is just dot in dot this dot dictionary dot then dot I dot set dot count comma 2 dot y dot, which means setting dict dot with dot index dot y comma comma comma, which means their count. It's okay if it duplicates. After all of this, I return our final dot count. So we have the algorithm complexity OATN here and the algorithm complexity OATN here. Thus, by running this algorithm, I need to return our original values. In this case, our answer should most likely be 10. That is, if considering repetitions, it should be 10. So it is indeed 10. To simplify or complicate and solve the task where the order is important, we will store, for example, a separate dictionary for these numbers, which will contain the indices and simply compare the elements by their indices. That is, if there is an element greater than a certain value, then we will proceed accordingly. If there is more of this, then in that case we will do it this way. Again, all these variations are described and very easily lead to the desired solution for solving without repetitions. With that, the theoretical and practical parts on binary search have indeed come to an end. Subscribe to our channel and join our Telegram.
Want to become a great programmer? Subscribe to our Telegram channel.